There's this incredible, invisible world happening all around us every single second. It's the world of sound. From the tiniest whisper to a massive concert, it shapes how we experience pretty much everything. And it's all built on some really fascinating physics. So let's jump right in and explore the science of how we hear the world.
So let's start with the biggest question of all. We hear it, we feel it, we make it all the time, but what is sound, really? At its heart, it's a type of energy, a physical thing that moves through the world in a super specific way.
And to really get that, we have to talk about waves. Nope, not the kind at the beach, but something just as powerful that travels through air, water, even solid objects. Let's break down exactly what a sound wave is.
Okay, so here's the official definition our sources give us. A mechanical longitudinal wave. Now, I know that sounds a little technical, maybe a bit textbooky, but the idea behind it is actually pretty simple. Let's unpack what those two words, mechanical and longitudinal, actually mean.
First up, mechanical. All that means is that sound needs stuff to travel through. It needs a medium, like a solid, a liquid, or a gas. This is exactly why there's no sound in the vacuum of space, like in the movies. There's just nothing for the wave to travel through. And longitudinal, well, that describes how it travels. Picture a slinky. If you push one end, you see a compression wave move down its length. That's kind of what sound does to air particles. It pushes them forward, and they bounce back. That back and forth motion in the same direction the wave is going is what makes it longitudinal. And what's really cool is that no matter what it's traveling through, its frequency, which is what we hear as pitch, always stays the same.
So that leads to a great question. Just because a sound wave is out there, does that mean we can actually hear it? Well, the answer is a big fat no. Turns out there's a whole spectrum of sound, and our ears are only built to pick up a tiny little slice of it.
We measure a wave's frequency in a unit called hertz, or Hz. Down at the super low end, below 20 hertz, you have infrasound. Think of things like earthquake rumbles that are just too deep for our ears to register. Then, way up high, above 20,000 hertz, you've got ultrasound. This is the stuff that bats and dolphins use to see the world. And right there in the middle, that's our sweet spot, the audible range. From about 20 to 20,000 hertz is the sound we humans can actually hear.
Okay, so we've got what sound is and what we can hear, but how does it actually move around in the real world? It's not just a straight shot. Sound waves are constantly interacting with everything, and they mostly do it in two main ways. They bounce and they bend. These two properties, reflection and diffraction, pretty much explain everything about how sound travels. Reflection is the one you already know. It's an echo. A sound wave hits a hard surface, like a wall, and bounces right off. Diffraction is a little more subtle, but it's just as important. It's the wave's ability to actually bend around things that get in its way. Let's look at a couple of real-world examples. If you've ever seen or used a megaphone, you've witnessed reflection in action. That classic cone shape isn't just for looks. It's designed to catch all the sound waves coming from your mouth and reflect them forward, focusing them into a single powerful beam instead of letting them spread out everywhere. It's a super clever use of sound reflection. And you experience diffraction literally every single day. Have you ever heard someone talking in the next room before you actually see them? Yeah, that's diffraction. The sound waves from their voice travel to the doorway, and instead of stopping, they actually bend around the corner and spread out into your room. It's the reason you can hear things that are just out of sight. So, we've covered the physics of how a single sound wave works, how it bounces and bends, but what happens when we humans start organizing those waves in a specific, intentional way? Well, we get something that's been part of our culture for thousands of years. We get music. So how do you get from just plain sound to music? It's pretty amazing, but it really comes down to math. A musical scale is basically just a set of notes whose frequencies have very simple, pleasing mathematical relationships. For instance, a note that's an octave higher, like the first saw and the last saw on this scale, has a frequency that is exactly double the first one. Our brains just love those simple ratios. Each step here, from saw to re to ga, is a precise frequency. By arranging sound waves into these beautiful mathematical patterns, we turn what could just be noise into the incredible structure of music.
And there you have it. We started with a simple vibration and ended up at the building blocks of music. So, the next time you hear an echo bouncing off a building, or you hear a conversation from around a corner, or you just put on your favorite song, maybe you'll hear it all a little differently. Now that you know the science, what new things will you start to notice in the sound of the world around you?